Okay, good day. This is Math 140 College Algebra. I'm Professor McCulley, and this is lesson 5-1, Rational Root Theorem. Let's get right to it. All right, today we're going to use the fundamental theorem of algebra to determine the number of zeros of polynomial functions. We are going to find rational zeros of polynomial functions. We're going to find conjugate pairs of complex zeros. We're going to find zeros of polynomials by factoring, and then we're going to use Descartes' rule of sign and the upper and lower bounds to find zeros of polynomials. So let's get to this. Let's define some stuff first. First, the fundamental theorem of algebra: if f of x is a polynomial of degree n, where n is greater than 0, then f has at least one 0 in the complex number system. So what that basically means is this, is that if you have some polynomial y equals f of x, then there must exist some value c, x equal to c, such that f of c is equal to 0. All right, there must be at least one complex number that you can plug into that function and get 0 out. All right, the linear factorization theorem says this: if you have some function that is of degree n, where n is greater than 0, then f has to have exactly n different factors. And they can be written as, and when I say n different factors, I mean linear factors, meaning x minus c sub 1, x minus c sub 2, and multiplying all of those out together, where c1, c2, all the way up to cn is possibly a complex number. And again, complex number could be a completely real number, a completely imaginary number, or a mix of both, a plus bi type of a thing. The rational zero test is basically this: if you have a polynomial that has integer coefficients, and so a sub n minus 1, a sub 2, a sub 1, a sub 0 in this general polynomial, these values have to be integers, and those are positive or negative counting numbers. And they must, if you have a rational zero, and remember what a rational number is. A rational number is a number that can be written as a fraction. RATIO, ratio, is a fraction. P and Q have no common factors other than 1, and we don't really worry about this a whole lot. We'll divide it out eventually. P is a factor of the constant term, and the constant term right here, there's your constant term. So that constant term is a sub 0, and the leading coefficient is the coefficient in front of the highest degree term. So here's my highest degree term, so a sub n, that is going to be my leading coefficient. Complex zeros occur in conjugate pairs. If you have a polynomial f of x that has real only coefficients, that means all of the coefficients are real numbers, okay? And they could be fractions, decimals, radicals, whatever, but they have to be real numbers. If a plus bi, if you have one imaginary in that particular situation, then you must also have its conjugate in that situation. And I will show you a situation where that happens, where you have complex conjugate pairs. I think we're two examples. So here's a factoring example. It says find all the zeros of the function and write the polynomial as a product of linear factors. Okay, we can do that. And so here I see a quadratic form. And I know that it's quadratic form because I got 1, 2, 3 terms. The degree of the second term is half the degree of the first term, and the last term is constant. And so I'm going to try and factor this thing because the leading coefficient is 1. And I ask myself, are there two factors of 100 that add up to negative 29? And clearly there are. Negative 5 times, or excuse me, negative 25 times negative 4 multiply to positive 100, and negative 25 plus negative 4 add up to negative 29. So we can rewrite this as x squared minus 4 times x squared minus 25, and these are both difference of squares. All right, and so a difference of squares is a squared minus b squared, and we know that that thing factors to a minus b times a plus b. And so this one here, I've got my a squared is x squared, and I have my b is 4. So x, or yeah, A would just be x, and then b would just be 2. So I have x minus 2 times x plus 2. And then same thing here for 25, or x squared minus 25. I'll have x, and then if b squared is 25, then b is just going to be 5. So I'll have b minus 5, and then I'll have b, x minus 5, and then x plus 5, like that. Okay. This is my product of linear factors. Each of these factors is a linear. The degree is 1 for each of those terms. And all of these are multiplications. So this is my product of linear factors. And that would be the answer to this particular question. Now, what happens if the question was find all the zeros? All right, so if I was asked find all the zeros, I'm going to do all of this. I'm going to say, hey, that's quadratic form. I'm going to see difference of squares. I'm going to get down to a product of linear factors. I want to find all the zeros. Those are going to be the values of x that make each of these factors equal to 0. So my zeros are going to be x equals 2, negative 2, 5, and negative 5. Now, there are going to be questions on the test and the exam where they ask you to do the difference. All right, it's the same basic work, but you have to understand the difference between a product of linear factors and the zeros. That's what those different types of questions ask. All right, the next one, and here it says find all of the zeros. Following function, write the polynomial as a product of linear factors. So the first thing I do is I look at this thing and I want to try and factor it if I can, because I don't want to do a bunch of work if I don't have to. Unfortunately, factors of 8, 2, 4, and 8, I can take a 2 out of that. I can take a 2 out of this one. I can't take a 2 out of the 9. That's no good. I look to try and do some grouping, so the only common factor here would be 2x squared, which would leave me 4x minus 7, and I could take a 9 out of this, which would leave me 2x minus 1, and those things are not the same, so I can't do grouping. So unfortunately, I'm going to have to use the rational root theorem here. I'm going to have to find the list of factors, F-A-C-T-O-R-S, spelled correctly there, Macaulay. Find the list of factors for P and Q. So my factors for P, all right, my factors for P are the factors of this thing. So I have plus or minus 1, plus or minus 3, and plus or minus 9. All of those integers divide negative 9 evenly. Then I want to find my values for Q. And my values for Q, I'm looking for that thing. So those factors are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. And so the next thing that I want to do is I want to find the quotient of all of the P's over all of the Q's. So find the list of P over Q. All right, so this ends up being pretty long. So P over Q. I'm going to go all of my P list over all of my Q's. So I have a long list of combinations. So 1 over 1, 3 over 1, 9 over 1. Those are all just going to be the integers 1, 3, and then 9. So 1 over 1 is 1, 3 over 1 is 3, 9 over 1 is 9. And then I go over to 2, and I go 1 over 2 is a half. 3 over 2 is 3 halves, and 9 over 2 is 9 halves. And none of these reduce down to any in that list. I'm going to go over to my 4, and I'll go plus or minus 1 over 4, plus or minus 3 over 4, and then plus or minus 9 over 4, and none of those reduce to any of the ones that came before it. So I got to have those. And then I got to go all of these over 8. So plus or minus 1 over 8, plus or minus 3 over 8, and then plus or minus 9 over 8. Now notice, I am done at this point, and none of these go on top. It's just the P's over the Q's, and that's it. You're done. Now, that's not even that much better because I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, plus or minus times will make me times 2. So I've got 24 different possible zeros. Since the degree of this polynomial is 3, there can only be 3 zeros total. Excuse me. And this thing only gives me the rational zeros, the possible rational zeros. That's what this list is. Oops, get my thing back there. All right, that excludes all of my just decimal answers that can't be written as fractions, irrational numbers. All of those are excluded. So clearly I have more than I can possibly use. So I'm going to go to my graphing calculator to try and reduce that list. And so I put this equation in here. It's 8x to the third minus 14x squared plus 18x minus 8, and then I've graphed it on a standard window, and I get this thing. And this thing here, well, that kind of concerns me, okay, because I know that this is a third degree polynomial, and the leading coefficient is positive, so the end behavior is down to the left and up to the right. And from negative 10 to positive 10, it looks like there's only one real zero. All right, now I'm going to guess, let's guess 3/4 maybe. I think 3/4, let's try that. And so I'm going to divide out 3/4, and I'm going to go 8, negative 14, negative 18, and then negative 9. All right, and so what am I going to do here? I'm going to try and divide out 3 over 4, because that's my guess. I think 3 over 4. So I bring down my 8. 3/4 of 8 is 6. 6 and negative 14 would be negative 8. 3/4 of negative 8 would be negative 6. Negative 6 and 18 is going to be negative 24. Oh, made a mistake. I made a copy error here because I have a plus. This has to be a plus. Oh, thank goodness. I was getting worried there. So let's fix this. Oh, thank goodness. Okay, so 8 times 3/4 is going to be negative 6, which will be 12, and then 3/4 of 12 is 9. That gives me 0. Oh, thank goodness. All right, so at first glance, you're going to say x minus 3/4 is your first zero. And while that's okay, and we can get those other zeros, it'll just be easier if we rewrite this thing, because I'm going to factor out that 8 there. So I'm going to rewrite this thing as 4x minus 3. That'll be my first one. All right, now clearly, it looks to me like there's only one real zero. If there's only one real zero, then the other two have to be complex imaginary values. So what I'm going to do is I'm going to take this remainder here, this quotient, this 8x squared minus 8x plus 12, and I'm going to put it into the quadratic formula. And so that's going to be x equals 8 plus or minus the square root of negative 8 squared, but I'll make it positive, minus 4 times 8 times 12 all over 2 times 8. So I get 8 on the outside, and then again, just because it's a big number and I want to keep it moving, I'll go 8 squared minus 4 times 8 times 12, and I get negative 320. 4 times 8 times, so I get square root 320. All right, all over 28. Now, clearly, I can divide a 4 out of that. Let's see, I can divide a 16 out of that. Let's see if that's the biggest thing that'll divide out of that. And it's negative, so don't forget your negative there. Divided by 16, is that the biggest number? Get 20. So I actually can take negative 340 or 320. I think I can get a 64 out of that. That'll leave me 5. That's 64 is the largest. That'll work. All right, so I've got x equals 8 plus or minus the square root of 64 times negative 5 all over 28. And, oh no, I'm sorry. This should be 2 times 8 because it's 2 times a, and our a value was that there, so we're good. Okay, so 2 times 8. And so I get x equals 8 plus or minus, the square root of 64 is 8. Take the negative out and make it I. I can't take the square root of 5, so I leave it there. And then I get 16 on the bottom. 1, 2, 3 terms all have factors of 8 in them. So I can take an 8 out of all of them. And that'll give me 1 plus or minus I square root of 5 all over 2. And these are my zeros. So my linear factors, my final list of linear factors will be 4x minus 3 times x minus 1 plus or minus I square root of 5 all over 2, and then x plus, oops, I didn't want to write it like that. I apologize. I'll write it correctly. X minus the quantity 1 plus I square root of 5 all over 2, and then x minus the quantity 1 minus I square root of 5 all over 2. And that's my list of linear factors. All right. I wouldn't want to multiply these out. Next, it says, given that 3i is a zero of the following function, finding the remaining zeros of the function. So they say that 3i will divide this thing. And you'll notice the coefficients are 1, 1, 9, and 9. So complex zeros occur in conjugate pairs. So that polynomial that we just did had real coefficients. All of these numbers, 1, 1, 9, and 9, are all real numbers. So I know that negative 3i must also be a zero. So I'm going to go 1, 1, 9, and then 9. I'm going to divide out 3i. So I bring down my 1. 1 times 3i is 3i. I add these two together and I get 1 plus 3i. And so 3i times 3i is negative 9i. And then 1 times 3i is 3i. And so I get negative 9i, and I should put a square there, I'm sorry. 3i times 3i is 9i squared, and that should be positive. It's going to become negative 9. You know what? Let's start over, and so you can see it a little bit better, and I'll explain it. So I know that I got to get some of this to cancel out, and I know that 3i times 3i is going to be 9i squared. And then, so 9i squared, 3i times 3i is 9i squared. And then this becomes 9 times negative 1. And that gives me negative 9. All right, so 3i times that 3i gives me negative 9. And I need that negative 9 because I'm going to get that to cancel out. And then 3i times 1 will give me 3i. And then when I add these together, I get just 3i. And then 3i times 3i is again 9i squared, which we know is negative 9. That gives me 0. Now, again, because I have all real coefficients, I know that negative 3i must also be a 0. So I bring down my 1. 1 times 3i, or negative 3i, is negative 3i. And when I add those two together, I get a 1. Negative 3i times 1, and it gives me negative 3i there. I add those together and I get 0 again. That means that this, what's remaining after I divided out x minus 3i and x plus 3i, is going to be just x plus 1. And so the 0 of this thing is going to be x equal to 0. So my remaining zeros, because that's what they asked me for. They asked me to find my remaining zeros. They give me 3i. Negative 3i is also one of the zeros that we had to find. And 1, negative 1, I don't know why I put x equals 0. X equals negative 1 is going to make that 0. So negative 1. And I get those are my remaining zeros. Okay. Well, I think that's it for this particular one. I meant to delete that slide there. The Marvel fun fact of the day: in Spider-Man Far From Home, Mysterio states that his Earth is 616, which is the main Earth timeline in Marvel Comics. The reason Marvel writers chose the number 616 is to show that our Earth has no particular significance to it. They just wanted to show that any reality is just as valid. Well, I know that was a long one, folks, but that's all I got for today, so have a good one. Goodbye.